is fine. Looks like it is recording now. Yeah, it is recording now. Fine. So okay. So yeah. So what were you asking? Assignment 11,
Assignment 11 in the ninth question.
ninth question.
So values of mismatches VT1, VT2 they are given,
Uh-huh.
but in the analysis the final answer is by considering the standard deviations of these mismatches. So how to get the standard deviations if voltages are given?
Let's see.
Suppose if we take the voltage as it is and it gets cancelled. And see, actually one more doubt we have. So while considering this mismatch, sir told that it is not necessary to consider the change, just you consider the magnitude of the change.
Hmm.
If that is the case, in one case we may get 0, in one case we may get twice some value, something like that, sir.
Okay. So
So,
what I will do is I will try to explain. Okay. So where you uh, in the where you present in the last or last to last class? I mean tutorial.
no, sir.
Okay. So we will what we will do is I will quickly cover some things here. Okay. I'll try to solve an example here of this guy. Okay.
Sir, please clarify this question, sir, first. Uh, uh,
Yeah.
Question number 9 in assignment 11.
Question number 9 assignment 11 is something that you have to do on your own, but yeah, that is what I told.
See,
No,
see I'm asking
I
about
will
the values only, sir.
explain. I will explain. Hold on.
Okay.
Okay, I'll explain. Fine. Yeah.
Okay, sir.
Before that, the guy who asked me a question about from assignment 10. Let me clarify that one. Yeah. So the thing was that yeah. So determine the position of dominant pole. Right. That was the question.
Yeah.
Right.
Yes,
Now
sir.
this dominant pole thing, they have clearly mentioned you have to find the dominant pole. Right. So
Yes, sir.
there may be different poles in the system, but you have to find only a dominant pole. So I guess dominant pole is simply because of the CL only.
Sir, 1 by R naught is also R naught is considered as one mega ohm, sir.
Yeah, but it
Ohms.
doesn't matter, na. But it is R naught is 1 mega ohm, but effectively when you find out the this thing, uh, when you find out the transfer function between V out and V in, that is figure 1b. Okay,
Okay, sir.
in that
Yeah.
when you find out transfer function between V out and V in, you will see that. Oh, sorry. When you find out the open loop gain, okay, for this particular loop, okay, then you will see
Yes.
that the dominant pole will come out to be because of R out and CL only.
Sir, because of the values, no, sir. But I consider the values R out CL, sir, and R naught and C naught. Here, R naught and C naught will be less, sir. 1 by R naught and C naught, or less than 1 by R out and CL.
Yeah, so why did you say that? Why do you say that the pole will be 1 by R out, R naught into C naught? Why do you say that? There will
Sir,
not be a pole at R naught by C naught or 1 by R naught C naught. It will be a 0 at 1 by R naught C naught. Okay.
okay, 0, sir.
Yeah, it will be a
Sir,
0. It will not be a pole.
okay. In order to find out, we have to do that complete analysis, sir. V naught by V.
No, no. You have to first break the loop, find the open loop gain, okay,
Okay.
and then you have
Yeah.
to find out where are the poles in that.
Okay, sir.
Okay. Yeah. So let me.
Sir, I also have a doubt in assignment 10. One
Yes.
question.
Go on. Go on.
Sir, the question number it's 6. To find the CMR. Sorry, question number 5. Find the common mode gain at 100 kilohertz.
One second. One second. Let me. Looks like a lot of people, a lot of doubt here. So. Is my screen visible?
Yes.
Yeah. So which question? Question 6.
Question 5. Question 5.
Fine. Define the common mode gain of the op amp figure 1A at 100 kilohertz. Yeah. So what is the problem here?
Sir, so basically in the lectures, Nagendra sir explained about the transfer, finding out the transfer function with the differential inputs,
Yeah.
right? So
Yeah.
we were able to find the differential gain at 100 kilohertz, or that will not change even. But
Yeah.
what about the common mode gain? How do we exactly do the analysis for
I
that?
think I covered this part, right? What is common mode gain? When you
When
apply
we apply
common mode,
B in CM,
yeah, both at both the inputs, at this
yes,
input, right? and at this input, both places you apply a same common mode incremental voltage, right? A small incremental voltage called VCM,
Yes.
small VCM,
Yes.
right? And then you
Right.
find out what is V out, and
Yes.
then you say what is V out by VCM, and since you have to normalize it, right? So you have to apply VCM by 2 at one input and also at other input VCM by 2 only. Okay.
Sir, but like the method for that is that if we split it into half circuit, then I was not able to do the half circuit analysis over here. Or is there some other easier way?
Now how do you split it into half circuits?
No, but that's what I was trying to do, but I was not able to do it over here
Yeah,
because
so
it's not
that's
exactly
what
symmetric.
you can ideally cannot do a half circuit analysis here because these two halves are not symmetric. Okay, these
Yes.
two halves are not symmetric, so you cannot do that. But there is a neat trick to get around that problem for common mode signals. So that is covered in week 12. Okay, I would suggest you can go through week 12 lectures once. Okay,
Okay.
that is covered in week 12 where there is a neat trick to find out
Okay.
what is the other way to do this is that you can use principle of superposition. Do not assume any half circuit or anything. Do a full analysis. Okay, do small signal analysis, assuming there is input VCM at this side. Okay, and this side is grounded, and then ground this side in the other case and put an input here, and then find out what is V out for both of them and add them. Okay,
Okay. Okay.
these two
Thank
things you
you.
can do, and you'll find out things. Okay,
Okay, sir. Thank you.
Sir, I have one doubt, sir.
yeah, go on.
Sir, these problems are so lengthy, sir, and in the final examination, if we find such problems, it may take a longer time.
Uh-huh.
Uh, shall we expect similar problems or
I
problems
cannot.
which
I
can be
cannot.
solved
I
within 3 hours?
no. I cannot say. I do not know anything about that because I do not handle these things. I have told many
Okay.
times now. I mean, these things are handled by the these things are logistics and they are handled by the IIT Madras only. I guess because and that is handled by Professor this Anirudhan sir, and he only knows how things will be. Okay, I do not know. Okay,
Okay. Okay.
but I can assure you that these questions are for practice. Okay, and the questions there should be doable in the time limit that has been that will be allocated to you.
Yes, sir.
Yeah, so don't worry about that.
The,
Focus.
the one out.
Yeah.
For when we have to consider the op amp as it is, we have to just break the loop and consider CL also, right?
It is clearly mentioned here, right? I mean, determine the position of dominant loop, dominant pole of figure 1b, right? And they have also written that consider the loop gain for this question. So, what is meant by that? You have to break the loop and have to consider this capacitor CL here.
For the first different determine the differential mode output resistance.
Where is that?
I mean, we can't actually assume the tail node to be at ground, AC ground, if that capacitance were not connected to the output of this transconductor, right?
Come again? I didn't hear.
I mean, without CL
Uh huh.
connected to VO, we can't actually say the tail node would be at AC ground,
Who
right?
said that? I mean, why?
Only then
Actually,
would.
you cannot actually cannot say anything about tail node here. You cannot say that tail node will be grounded here for differential input. You cannot say that.
Even if the capacitor CL is connected to VO.
Yeah. Yes.
Okay, okay.
There is tail node is grounded when tail node is grounded. When is that the case?
Symmetric.
Yeah. This.
But then again, Nagendra sir did show case where if the um, resistance looking into the drain of M3 or the drain of M4, if it's very less, then it would be more or less symmetric, and Vx, that is the
Yeah,
tail node,
that
would
is true.
be.
I mean, the approximation is always there, right? So, yeah,
Yeah.
approximately this is grounded. This will not move much, but still, I mean, I am saying to be very precise. This is not. You cannot say this is grounded. Okay,
Oh, okay.
fine.
That's fine. But
Yeah.
then again, when you have to consider the op amp, it means the transconductor plus the output load capacitance, right?
I don't think so because they have not mentioned something like that. I mean, this is always a confusion. So figure 1a, when they said, I don't think they want you to consider this CL. I mean, they do not want you to consider this connection at all. This feedback they do not want you to consider. Okay, they only want you to consider this figure 1a op amp as it is. That is my guess.
Okay.
Yeah. Fine. So we
Sir,
can.
one small question, sir.
Yeah.
Sir, in noise analysis, sir, if two currents are correlated, sir, for suppose I plus I by 2, sir,
Uh huh.
after squaring it, it become I square plus I square by 4 minus 2 E of I1 plus E of I by 2, sir. After that, how to solve it, sir?
If the two noise sources are correlated, or
Yes, sir.
saying correlated, right? Not
Yes, sir.
uncorrelated.
Yeah.
Okay, so if the two noise are not uncorrelated, they are correlated, then you have to find out what is that variable expectation of, basically what is the cross correlation. You'll have to find out, and
How, sir?
if there will be some information given to you for that. Okay,
Okay, sir.
yeah, but please note that if the two noise, if these two noises are always it's always the case that if two noise voltages or current whatever, if they originate from two different devices, okay,
Yeah.
two different devices, if they originate from, then they will be uncorrelated.
Sir, in assignment, sir, I'm getting for one transistor only, I am getting I minus I by 2, sir.
Which assignment I was talking about?
Assignment 8, sir.
Okay, let's see what is assignment 8.
1 minute.
Okay, so what is the problem here?
So 1 minute, sir. Assignment 9. Assignment 8 only, sir.
Yeah, so what is the problem here?
1 minute, sir.
Is my screen visible to you?
Yes, sir.
Yeah, this is assignment 8.
In assignment 8, sir, that W by L ratio, sir. Seventh question, sir.
Yeah, what is the W by L is equal to M1 R naught to the input of the thermal voltage density?
That
Yes.
range also 4 to 5, 360 had given, sir. I don't know.
Figure 2. Okay, figure 2 is the thing. This is figure 2, right?
Yes, sir.
And what is the, yeah, so I have to find out what is there some issue here?
Yes, sir. We're not getting in that range, sir. That is
Okay.
Actually, we are getting to 1 point something, right? Isn't it?
1.4, sir.
1.4, yeah, but
So
it's not.
did anyone get the correct answer for this question?
Yes, sir.
Yeah, so what were no, the person who was not getting the correct answer, what were you doing?
Sir, we are equating that 4 by 3.
What is the contribution of RD to, so what is the question here? Equal noise contribution from M1 and RD to the input referred thermal noise voltage density, right?
Yes, sir.
So first you have to find out what is the noise contribution of RD at output, and then you have to input refer it, right?
Yes, sir.
So what is the gain from V in to V out? What is the gain?
GM.
GMRD by 1 plus GM.
Yes, sir.
GMRD by
1 plus GM RDS.
you have to assume infinite output resistance for M1. Is it given the question like that? Yeah, it is given. Yeah, it is GMRD by 1 plus GM. Is fine. And nice, right. And what is the output? So what is the noise current due to RD at output? V out at this output.
4 by 3 KT by KTR into GM square, sir.
No, I am only asking about the noise current density of this. So this is basically 4
4 by 3 KTR, sir.
4 by 3. No, not 4 by 3. It will be 4 KT RD, right? Because
Yes, sir.
for RD it is 4 KT
Yeah.
4 KT by RD, right?
Yes,
4
sir.
KT by RD, right?
Yeah.
And then you have to and what is the noise voltage? 4 KT by RD multiplied by total output resistance, right? Which is RD square.
Yes, sir.
So it will be
Yeah.
4 kT RD only, noise voltage of due to RD, right?
Yeah.
When
Yeah.
you input refer it back to the input, so it will be what? 4 kT RD divided by
Gain square.
gain square, right?
Gain square.
So it
Yes,
will
sir.
be Gm times RD whole square into 1 plus Gm RS the square whole square, right?
Yes, sir.
And that is due to RD. Similarly, due to M1 you have to find out. So what will be the noise contribution due to M1? I think we solved this circuit in
Sir, I'm getting I minus I by 2, sir. By splitting the current, sir, because RS equals to 1 kilo ohm, sir. GM 1 by GM is also 1 kilo ohm, sir. So it will be split into RS and that transistor, sir.
fine. So what?
And other will be directly going to that V out, sir. So I minus I by 2 I'm getting, sir.
No, you're right that half of the current will flow through M1 and half will flow through. So only half of the noise current of M1 will actually contribute to noise at the output. That is
So, but
fine.
here you are taking the current splitting, no, sir. Two current sources and one is grounded in the middle.
Yeah. So that is
One
what.
current source will flow completely through that output, sir, and other only half current will be flowing through that output. I minus I by 2 I am getting, sir.
Okay, 1 second. Let's do this. Uh, stop sharing. Quickly, let me do this. Uh, is my screen visible?
Yes, sir.
Fine. So, let's add a page here. Discussion. Yeah, fine. So the question is this, right? I mean, you have this RD, you have this RS, correct? You have this input, this output, and then you have to find out what is the total and what should be the W by L, right? Such that the noise, or rather input referred noise, this is assignment 8, right?
Yes, sir.
Yeah. So input referred noise voltage due to M0 and RD are same, correct? Fine. So now let's do this. So when you so already due to RD, what is the contribution due to noise due to RD input referred. So SV in due to RD is what? 4 kT RD divided by Gm times RD whole square 1 plus Gm times RS whole square, right? Correct? Now noise voltage at the noise contribution of M0. So how will you find out noise contribution of M0? First you ground everything, right? All the independent sources. So this is RD, this is the MOSFET, then this is also grounded here, or this RS here, and this is a noise source here. So let's say this is what is this, 4 kt gamma 4 by 3 kt into gm, right? Is it correct?
Yes, sir.
Yeah, fine. Now tell me, what did you do?
Sir, I did current splitting, sir.
Correct. So at this point current will split here and here, right?
Yes, sir.
So what current will what will contribute to the, oh by the way, this output here, this will also be grounded, right?
Yes,
I'll
sir.
ground it for first I'll find out the total current and then I'll multiply it with the output resistance. Fine. So what is the total current that will be flowing at the output? I mean into the ground here.
Sir, here one current source has to split it to two current sources, no, sir?
Yeah, yeah. So one is going in this MOSFET, right? And one is
Yes, sir.
going into RS, right?
Yes,
So
sir.
what is the part that is more flowing into MOSFET and what is the part that is flowing into RS? So what is the
Uh,
GM here? What is the GM of this MOSFET?
1 milliohm, sir. RS is also 1 milli.
Fine. So let's assume GM is GM, okay, and RS
Yes,
is
sir.
RS, right? So how much? So basically you have current splitting, current which
Half,
is
sir.
4 kt GM over 3. This current will split into uh, GM
Half,
and
sir.
1 over RS thing, right? And what
Yes,
is the
sir.
ratio of splitting?
Half.
No, no, in terms of GM and RS. So it will be sorry, in the RS it will be 1 over RS divided by 1 over RS plus GM, correct?
PM. Yes, sir.
And that is equal to what? 1 over GM RS plus 1, correct?
Yes, sir.
Right now?
Yes, sir.
Yeah. So so the current that will be flowing there will be what? 4 kt sorry, let's this is basically current square, right? This is SIN square, this is SIN, right? Spectral density.
Yes, sir.
So you'll have to find do the this square, right? Do you understand what I'm saying, what I'm doing here?
Sir, my doubt is, sir, here the current source has to be split into two sources, no, sir?
This is what I have done now here.
No, sir. I mean, in some videos, they shown that two current sources and in the middle it is grounded, sir.
Yeah.
Yes, sir.
Okay,
If
so
uh, if
let's.
that is directly not grounded, sir, they saw the two current sources and one is grounded in.
Oh, okay, okay, I understand. Okay, so that is so. But do you understand this? What I'm doing here?
Yeah, I understood, sir.
Understand? Do you understand? This I already took covered in one of the tutorials also. Okay. So by
Yes,
the
sir.
way, so from this let's understand. So this will be 1 over GM or GMRS plus 1, right? The current
Yes, sir.
ratio, right? And you
Yes,
have
sir.
to take its square because this is but effectively this is effectively ion square, right?
Yes, sir.
Correct. So what will be
Yeah.
the current density? It will be 4 kt gamma gm 4 kt gm by 3 into 1 over gm rs plus
Plus
1
one.
whole square, correct?
Yeah.
This will be the effective current that will flow at the output, correct? And now you have to
Yes, sir.
multiply it with the this RT, right?
Yes, sir.
So total input preferred noise due to M0 will be what? So 4 kt gm by 3 multiplied by 1 over gm rs plus 1 the whole square multiplied by RT the whole square, correct?
Yeah.
Correct.
Yes, sir.
And then divided by the total gain, right, which is gm times
Yeah.
RT whole square divided by 1 plus gm rs the whole square, correct?
Yes, sir.
So this and this went, correct? This and
Yeah.
this is gone. So this is basically effectively 4 kt gm by 3 divided by gm whole square, which is 4 kt by 3 gm, correct?
Yes, sir.
And now you have to equate both of them. So you have to equate what, 4 kt by 3 gm and other one is what, this is the other one, right?
Yes,
4
4
kt
kT
RT.
RT. That
So
gain equals to 1 minute.
4 kt RT divided divided by gm times rd square 1 plus gm rs square, correct? So when
Yes,
you
sir.
equate these two, I guess you should be able to find out a constraint on gm. You should be able to find out how much gm should be, and from there you can find out what is w by l.
Okay, sir. Yeah.
You cannot say anything about I mean gm you cannot say a priori, isn't it? They have asked you for the w by l ratio simply because they want you to find out what will be the gm. Okay, you cannot
Yes, sir.
assume that gm is equal to 1 over rs. That is not a correct assumption.
Okay. Yes, sir.
From here you have to find out what is the gm, and from
Yes,
there
sir.
you can find out what is the w by l required to achieve that gm. Okay.
Yes, sir. One question, sir. Final. That is in current sources, sir. Sometimes they had taken the two current sources and the equal and one in the middle. One is grounded, sir.
Yeah, I
So when
understand.
to do it and when not to do it. That
No,
one, sir.
this here it can be done. Okay, so let's do that also. So the question was this, right? This was RD, this was VDD, and you have this MOSFET. This is basically this has to be okay. So I am focusing on the noise due to
Most.
M0, right? So I will
Yes.
be grounding everything here. So this is the noise source, correct?
Yes.
Fine. So this is RS. Okay. This is M0. This is, let's say this is I naught. Or let's call this is IN. Okay.
Yes, sir.
So this IN, it you see this is connected between two nodes which are not grounded, neither of which are grounded, right? So you can
Yes, sir.
effectively do this for this. This is RD. Okay. And you have this MOSFET here. This is anyway grounded, the gate, correct? And this is RS here. And here what you can do is this this current source you can split into a series of two current sources. Okay, let's do that. So this is also IN, this is also IN. So if I do this from here to here, does it make any difference in the circuit?
No, sir.
Why?
Sir, here one current will completely flow through that output, sir. V out. That equals to IN. And
You see, yeah, correct. So basically, if you take only this, if you think about the terminal characteristic, basically, if you take this part separately. Okay, so let me change the color here. Okay, so if you take this part only, okay. So here also, if you take this part only, so for the part which is left, which is inside this highlighter, yellow highlight. So do you think anything is going to change for that if I
no, sir.
do this thing? So why is it not going to change?
Sir, KCL is valid.
Correct. So effectively the same amount of current is flowing, right, in both the cases.
Yes, sir.
Right now in this case it was IN, right, flowing here and going inside here, right? Here also it is flowing the same current is flowing. IN is flowing here and IN is coming out here, right?
Yes, sir.
Correct. So
Yes,
effectively
sir.
the terminal characteristics do not change when I do this, isn't it?
Yeah.
And now if I do this, now this node voltage, I do not this node voltage is of no consequence to us, right? I mean I can as well do this. So what I can do is this is RD, correct, and this is your MOSFET here is grounded. So this is RS, fine, and this one current source is here and other current source is here. What I will do, I will simply ground it here. Okay, this is IN, this is also IN. I can also do this, right? Because right in this case also the same amount of current is flowing here. IN is coming here, IN is coming here, right?
Yes, sir.
Right? Doesn't matter. And at this node also,
Yes, sir.
the effective total current that is going to flow here is IN, and current is coming IN. So effectively nothing changes when I connect ground here, isn't it?
Yes, sir.
Right? Now when I did this, now it is fairly simple, right? Because now it has been changed into something different. You see, this can be this is grounded here still. This is RD, and now this is RS, fine. But now this part, this IN is connected to ground here, correct? And here also
Yes.
there is an IN which is connected to ground. Fine.
Yes, sir.
And now when you try to find out what is the total output, this total noise contribution at the output, okay, now these two noise sources are not uncorrelated, they are correlated, okay. So
How to find that E into I1, IN1 into E IN2? So that's the question.
no, so they are exactly identical, they are not even correlated. This noise are exactly identical, isn't it?
Okay, sir. Yeah.
So when two things are identical, they will add and subtract exactly like you have seen in algebra, okay. There is no
Okay.
statistics involved.
Okay, sir.
Fine. So I guess that concludes it, right?
Yeah. Yes, sir.
So there was a question about week 11, right? Someone asked me. I guess Venkata asked me. So let's deal with that also briefly. Week 11. So
Sir, just a small request,
yeah,
like
yeah.
the discussions which you do in this, like the separate doubt solving problems which you take right now, can you upload the PDF of this also on the
I
drive?
guess I upload everything. The PDF,
Uh,
everything I
I
upload.
think I was not able to find for one week. Maybe it was my mistake,
No,
but
no.
just
This is always I upload everything which I covered here.
Yes, sir. Yes, sir. All are
okay, sir.
there.
Yeah. So check it thoroughly. Okay, you will see. I upload
Okay.
everything. Fine.
And sir, will this be the last doubt solving session or will
No,
happen one next
this
week
is
also?
basically there was this problem in there is this problem in conducting the session. So next week also will there will be a session, okay. And next week I will mostly be taking your doubts. I will not be covering anything on my own. So you come up with your doubts and I will be taking that. Okay.
Okay, sir. Thank you.
So
Thank you, sir.
this is basically week 12. Today is supposed to be week 12. So it's supposed to be the last one content wise. Next week you can simply ask me whatever you want to, because that is supposed to be the concluding tutorial. Okay. Anyway, so week 11 I would like to discuss week 11 thing. So there is this question which one person asked me. Yeah. So 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 I'll not be talking about the exact question, because that is not, I'm not supposed to do that. So what I'll be doing is I'll be taking an example here, okay, a similar kind of example. So the famous circuit, I will take the famous circuit, which is something which we have been seeing a long time from now. So okay, so this is VCM, fine. So this is the output. This is VCM plus some VIP, VCM plus some VCM plus some del B, VCM some del B, and this is V out. Okay, this is some V out. Fine. Now let's also split it in terms of some common mode, which is V out, and plus some small signal which is V out, small V out. Yeah. So now the now let's say you have calculated everything, okay. Let's say this. So in this case, when you want to realize, sorry, when you want to realize this amplifier, okay, so these two are supposed to be exactly same, right? M1 and M2 are supposed to be exactly the same, right? So they have to be, their threshold voltages and every property, every parameter should be exactly same, correct? W by L, threshold voltage, everything should be same for both M1 and M2. Similarly, M3 and M4, they have to be matched, right? Their threshold voltages has to be same, correct? So let me take this. These two have to be matched. And what I mean by matching? I mean by this is VTP W by L mu P Cox should be same, correct? Similarly, these two here, they have to be matched, which means VTN W by L mu N Cox should be same. Okay, so who asked me this question from week 11? Venkat, right?
Yes, sir, myself.
So do you understand this, right? They have to be matched. These two and these two have to be matched, correct?
Yes, sir.
Right. Now when they are matched, what happens? You see that the overdrive here is same, right? I mean in the bias condition at least. When delta V is not there, you see that the overdrive here and VGS here and VGS here is exactly same, right?
Yes, sir.
Correct? So let me VGS here and VGS here are exactly same, correct? That's okay. Similarly, you see that VGS here and VGS here are exactly same, correct?
Yes, sir. Yes.
And so if you assume that there is no channel length modulation, if you assume that CLM is neglected, in that case, because of this current mirroring here, which is current mirroring here, what should happen? You assume, you can safely say that same current flows here, right? In both the branches, correct?
Yes, sir.
And this V out, in absence of any small signal, this V out should be equal to this voltage, correct? This V out should be equal to, let's call this V1. Okay, so this V out should be equal to V1, right? In absence of any small signal. And
Yes, sir.
if everything is fine, right? In the common mode, this V out and V1 should be exactly same, correct? Now let's say that well, I will not say let's say, this is actually what happens. I have already said that this have to be matched, correct? Now what happens in reality is that this particular constraint cannot be exactly met. Okay, the two transistors which you see here and the two transistors on the top also, they will not be exactly matched. I mean, their threshold voltages will be slightly different from each other. Okay, fine.
Yes, sir. Yes.
Fine. So what happens is that in the presence of a small difference in threshold voltages, they are said to be there is said to be a mismatch present. Okay, basically in presence of any mismatch in the threshold voltage, basically mismatch. So what will happen? What do you think should happen? If the threshold voltage of M3 and M4 are different, what should happen? What do you think should happen?
Currents will be different.
Currents will be different, exactly, right? Now there is the current is not supposed to be different, isn't it? So when the currents are different here, let's call this I3, let's call this I4. If I3, so what happens in this case? I3 will not be equal to I4, correct?
Yes, sir.
Correct. Now what do you think is the immediate result of this? When I3 and I4 are not equal, this V out here will not be equal to V1, right? Even
Yes.
when there is no signal present here, even when there is only VCM here, okay, even then the V1 and V out will not be same, correct?
Yes, sir.
Right? Now yeah, so that is something which you do not desire, right? Because V out is supposed to be only dependent upon the input signal, I mean only the incremental signal, right? Or incremental differential signal. But here, even without applying any input, you are seeing that V out is a different value from its bias point, isn't it?
Okay.
So V out will slightly deviate from its bias point, and you will register it as an output because of some input, but actually you have not applied an input, right? So this is not desirable. So how do you model it? So what do you do in practice is, in practice there will be a lot of mismatch, okay? And how do you solve, how do you estimate what is the effect of mismatch? You will do it by assuming that, so basically there is this MOSFET here, and let's say the threshold voltage of this guy M3 and M4, let's say that M3's threshold voltage is slightly lower, okay? So this is here. This is M1. So let's say threshold voltage of M3 was VTP of M3 was equal to some 1.2 volts, okay? And let's say this VTP of M4 was what, 1.3 volts, okay? So and let's say this is the connection. So what do you think, which current should be higher in this connection? Which current, I3 in I3 and I4, which should be higher?
I3, sir.
Why do you say that?
The difference voltage is lower.
Correct, definitely. So effectively you see that the overdrive increases for M3, right? Because VTP3 is lower, correct? Right now?
Yes, sir. Yes.
Yeah. So how can you model it? You can model it by simply adding a voltage source. In which direction? Where should be plus and where should be minus?
Right side should be plus.
Correct. This should be
M4
plus, this
should
should
be
be minus.
plus.
Correct? And how much should be the voltage? And let's call this that's VTP nominal. Nominal should have been 1.2 volts only, okay? But due to some mismatch, this guy is increasing. So what should be the voltage here?
0.1.
0.1 volts, right? Correct?
Yes, sir.
Right. So this is the way that you model it. If there is a mismatch somewhere in the circuit and they have given you some values for the threshold voltages, this is how you proceed. This is how you model the mismatch. And now because and this mismatch here, it can be treated as small signal, okay? Because compared to the VCM, this is very small value. 0.1 voltage is very small, right? VCM will be of the order of, let's say, 2.1 volt or something like that. And with respect to that, this 0.1 is nothing, right? So
Yes, sir.
this is how you model it. So in the question of assignment 11 also, you have to do the same thing. You have to model it and then you have to find out whatever they have asked.
Okay.
So does that answer your question, Venkat?
Yes, sir. Yes, sir.
Yeah, fine. So
Sir, I have one question.
yeah, go on.
So this is related to cascaded current mirror.
Okay.
If I consider all the resistors, if I consider channel length modulation,
Uh-huh.
then I have to consider all the resistor RTS.
Okay. Okay.
In that case, the contribution of the noise will be not only for main current mirror, it will be cascaded. Cascaded current mirror also contribution will be there, right?
Yeah, right. Yes, it will be, yes.
Okay. Okay.
Yeah. Fine. So if there is nothing else, I will now like to proceed with this week's content. Okay. I've not covered anything till now. Fine. So let me go ahead and do this week's at least one problem here. So let me select which questions should I attempt here. Let's do this. Oh, I didn't mention the introduction. So anyway, I'll do this now. So like every time, this is analog IC design, and the instructor for this course is Dr. Shankaran Nidhan. he's a professor in IIT Madras, in Department of Electrical Engineering. Myself, I am the tutor for this course, both these tutorial sessions, and my name is Mayank Anupam. I am a PMRF scholar. Uh, I am currently pursuing a PhD at IIT Kanpur. Okay. So yeah, so this week you learned about the transistor level implementation. In week 12, you have seen the transistor level implementation of op amp, right? So this is a simple op amp, correct? There is nothing here in this particular figure. This is not a two-stage op amp. This is a simple single-stage op amp, correct? So the question is, figure shows the unity feedback configuration of an integrator studied in class. The integrator has been realized using a differential amplifier shown in the insert. So due to parasitic capacitance CP, the integrator has become non-ideal. So you know that this node here is there is no capacitor assumed, right, at this node here, correct? Or this node, right? We do not assume any parasitic capacitance, but now we have assumed some parasitic capacitance CP at this node here. Now neglect channel modulation here. Also you can assume GM of 1 and 2 and GM of 1 and 2 are equal, and GM of 3 and 4 are equal, and the relation between them is GM of 1 and 2 is equal to 2 times GM of 3, 4, correct? Now find the signs of A and B. First, let me ask you this question. So this is the final circuit that you are going to realize. You want it to be connected in negative feedback, okay? So tell me, in A and B, which should be plus and which should be minus? Which terminal should be plus and which terminal should be minus?
Sir, A is plus and B is minus.
How?
Sir, we can think as a superposition, like if we ground B terminal and increase A terminal,
Okay.
and so we can think as a like the drain of M naught is increasing if A is increasing.
Okay. It increases. Okay.
So,
Fine.
so, so D of M0 is increasing, so the D out will be increasing as M2 is in common gate configuration,
Fine. Fine. Fine.
and
Correct.
likewise the VS.
Right. Correct. Exactly. So basically A and B, in A and B, everyone understood, right? That A should be positive and B should be negative, correct?
So once repeat.
Yeah, so basically I am asking what should be the signs of A and B for this circuit here to be negative feedback. So you understand, this transconductor is basically this one only, okay? And you want to realize a negative feedback circuit here. So which should be plus and which should be minus? So A should be plus and B should be minus, because why? Because now how do you find out which should be plus and minus? You break the loop, right? Then you apply an input somewhere. So here you break the loop and then apply, let's say, a positive excitation here at A, correct? Let's say this that in A and B is negative, okay? So how will the circuit look like? This is B, let's say this is B and this is A, okay? Then now you break it here, you apply a excitation here, correct? Let's say this is a positive excitation, and you find out what is the sign that is going to return. So basically when it traverses like this, what is the sign of the thing which is returning? So here also when you apply an input here, so this node will definitely decrease, isn't it?
Yes.
Correct?
Common source.
Yeah, it is a common source, correct. So it will definitely, it is not a common source per se. It is source degenerated, isn't it? It is source degenerated.
Yes.
So this will definitely go down, okay? And when this goes down, the output, basically the thing that is going to come here, is also going to decrease, isn't it? So that is why when you applied an input which is increasing, the return is decreasing. So now that means it is the correct sign, isn't it? Do you understand?
Yes.
Yeah, fine. So that's easy. I mean, it's covered many times. This is fine. Now what is the effective GM of the differential amplifier DC and at very high frequencies? So what is the effective GM here of this transconductor? The transconductor that is shown in the inset here. What is the GM? GM means some output current divided by some input voltage, correct? Right now?
Yes, sir.
Yes. So you have to apply a differential input at the differential input, right, between A and B. So let's do that. Let's do this here. So this is VDD and this is your, sorry, this is PMOS. This is M0. This is, so let's say this is plus delta V, this is minus delta V by 2, delta V by 2. This is like this. We have applied a capacitor here, put a capacitor here, CP. This is the output. Fine. What is GM? GM is basically, you have to find out what is the total current here. Okay, so for finding the total output current, you can ground it. Okay, effectively in the small signal picture you can ground it. So right now I'm looking at the small signal. Okay, so VDD I have grounded here, and this is also grounded here. And find out what is the total current ISC, which is I short circuit, divided by the total voltage, which is delta V, right? So tell me what will be the voltage here. This is M1, this is M2, this is M3, this is M4, correct? Yeah, tell me what will be the short circuit current here at DC. At DC you can assume the capacitor is not there, right? Right now.
Yes, sir.
Yeah, so tell me what will be the short circuit current here.
Sir, GM the delta V.
GM delta V.
ISC at DC is equal to what? GM times delta V.
Delta V.
Delta V.
And what is GM is? GM of what?
M1.
M1 and M2.
On RM.
So you have to assume there is no channel length modulation, okay? No channel length modulation is present. So output resistance at every node is infinity, correct? Except for this particular node here. Right? Here the sorry. Fine. So you can assume there is no channel length modulation, right? So output resistance is infinity everywhere. So that is why the current is only dependent upon VGS of this, right? Here you can assume that there is this node is grounded incrementally. Can you tell me why I can assume that?
Because the drain of M2 is short circuited. I mean the resistance you're looking from the drain of M2 is 0, and from M1 is also 1 by GM, so that is also small. So from the approximation,
No, not like that.
you can tell me.
It's not like that. Tell me. You can assume. Tell me why. You can assume that.
If we look into the drain of M3 and M4, the resistance is very small. So effectively, of looking into these sources of M1 and M2, it's 1 by GM. 1 by GM,
Okay,
1
so
or 1.
okay. So let's understand this like this here. Okay. So you see that this source is common for both of them, right? Correct now. Source is common for both of them,
Yes, sir.
right?
Yes,
So let's
sir.
assume that this is
Oh,
VS.
yes, yes.
Okay.
If we put superposition, then the the drain of M0 will be 0. Yes.
Yeah, correct. So that is what I was saying. If you use principle of superposition, this will come out to be 0. But let's not let's also do this the more general way. So we have assumed that there is no output resistance, okay? So that the current flowing through this will be what? GM of M1, and by the way, GM of M1 and M2 are exactly same, right? So I will only use GM here for M1 and M2, correct? इसलिए GM times V or delta V by 2 rather minus Vs, correct? Right? And what is the current that is leaving this node here, which is flowing through this? This is in this direction, right? This should be what? GM times in this direction. What is the current in this direction? Okay, so that is confusing you. Fine. So what is the current in flowing through MOSFET M2?
The GM that times minus the delta V by 2 minus.
Right? And these two currents here, this current and this current, they should add to 0, isn't it? KCL should be applicable at this node, right? Because no current is, this is a perfect current source, right? This will be, this output resistance is infinity, isn't it? So this will be open, correct?
Yes, yes.
This is grounded, right? So there will be no current flowing through this in incremental sense, correct? So this have to be add to 0, isn't it?
Yes, sir.
So that GM and GM cancels, delta V by 2 minus Vs minus delta V by 2 minus Vs should be equal to 0. This and this go on. This looks like 2 Vs has to be equal to 0, which means Vs has to be 0, right? So if all the resistances are infinity, output resistances, or if you ignore CLM, then you can comfortably say that this node will be incrementally grounded in differential case, okay?
Yes, sir.
Yeah,
Yes.
fine. So fine.
Okay.
So now let's do this again. So what is the short circuit current ISC is? GM of M1, M2, or let's only call this GM, times delta V, right? Correct? Correct?
Yes.
Yes, sir.
Yes, sir.
So what is the, so which means what is the this thing? What is the effective GM?
GM1.
Is it actually equal to GM1, right? Hello?
Yes, sir. Yes. GM1.
Yes, sir.
So is this correct, by the way? Or is there something something wrong with this experiment? I mean, have I done some mistake here?
No sense, correct.
Some amount of current might go into the cap if there is some parasitic cap.
No, I have assumed that I'm doing this at DC.
At
Okay?
DC calculation,
So there's no parasitics involved here. So is this correct? Is it?
Yes, sir.
Are you sure?
Yes, sir.
Okay, so let's check this. Why did you say that it is GM? It is GM delta V and not GM by 2 delta V? I mean, the current which is going to flow here will be GM by 2 delta V, isn't it?
But sir, one component will also flow from into.
Yeah, that. No.
one component also current mirroring that.
Yeah, right.
That
So it is not exactly GM1. It will be GM2 times delta V plus whatever is coming here, right? So what is the current here? Current is GM1 times delta V by 2, right? That is the current flowing in this. That is mirrored here, right?
Yes,
Correct,
sir.
na? So what is the, okay, so mirroring ratio is same, right? And that is mirrored here. So this is exactly the same current, GM1 and then again GM1 by 2 times delta V, right? This is GM1 times delta V, correct?
Yes, sir.
Yeah, so it is not that these and these are two different currents. This is exactly the same current. One component is coming from M3 and M4. That is why it is 2 times GM1. Okay? Understood?
Yes, sir. Yes.
Yeah, so this is how it is. Fine. Now, so effective GM is effective GM is GM1, correct?
Yes, sir.
Now let's say I am talking at very high frequency. So you can assume all the capacitors are shorted. So our circuit was what? We had the circuit, right? And I will assume that M0 is basically a current source. Okay, I'll represent it as a current source. Okay, and this is delta V by 2, this is delta V by minus delta V by 2. Okay, now tell me what should be the ISC here?
GMO 1 by 2 into delta V.
How?
Because the CCP is short circuited, so the mirroring action will not occur.
Yes, correct. It's basically GM of 1 by 2 times, or GM of 1 into delta V by 2, right? Correct.
Yes, sir.
So uh, so effective GM, what will be the effective GM in this case?
GM 1 by 2.
ISC divided by delta V by 2, 2 times delta V by 2, right? So it will be GM1 into delta V by 2 divided by 2 times delta V by 2, which is simply GM1 by 2, correct?
Yes, sir.
Yeah. So you understood what is the problem with this capacitor? I mean, what does this capacitor do here?
Lowering the GM,
Correct.
so
So
that
effectively, the effective GM
steady
of the
state.
circuit, if you plot effective GM versus frequency, okay, so what will it look like? You start at very high value, and then after some time it will look like this. Okay, this is GM1 by 2, and this is GM. Okay,
Yes.
yeah. So now let's move on. So this is fine, correct? This is fine. So what is the loop gain? What are the location of poles and zeros in this case? Tell me. Oh, by the way, okay, yeah. So fine. Now tell me what is the loop gain. So let's do that here. So, third question, right? So you have the circuit. CP here. You have this capacitor here. And after this there is a buffer here, right? Yeah, this is buffer, right? A gain of 1. And now its output is connected to what? The negative terminal, isn't it? Which is this. Correct? And this is your Vn. Okay? So tell me what will be the loop gain here? What will be the loop gain?
So loop gain is 1.
Eh? No, no, I'm talking about loop gain versus frequency.
Oh, sorry.
What is the loop gain as a function of frequency? Tell me. How will you find the loop gain?
Sir, break the loop at anywhere and
Break the loop.
apply test.
Before breaking the loop, what should I do?
Bean must be grounded.
Grounded. This is should be grounded, isn't it? This should be broken.
Yes.
This should be removed, right?
Yes. Yes.
Yes, sir.
Now this is broken here, and I have to apply a test voltage here, right? Correct?
Yes, sir.
And I have to find out what is the V return here, correct? Tell me what will it be? Tell me.
So here two poles must
Okay,
be
so
there.
yeah, fine. So tell me now. So when I apply V test here, okay, and this is by the way hanging here, fine. So what is the looking in impedance here? It's 1 over GM, isn't it?
Yeah.
Yes, sir.
Fine? Fine now?
Yes. Sir.
Yes, sir.
Yeah. So yeah, so tell me what will be the current here? M1 M2 GM is same, right? So GM, let's call it GM1 only, right? Into a GM1 divided by 1 plus 1 over GM1 times GM1. This is source degeneration, isn't it? This is source degeneration, right?
Yes, sir. So here the channel length modulation is neglected, right?
Yeah, yeah. So it is already given in the
Okay.
question, right? You have to neglect channel modulation here.
Okay.
Fine. So this is GM2 divided by 1 plus GM1 into GM2, right? This is how it is. Multiplied by VT, correct?
Yes, sir.
Correct. And this is current due to current due to M2, right? But there will be a current component due to M4 also, right? Here also. So what is that? What is I4?
Only that it will be mirrored.
Yeah. So whatever current flows here, right? Whatever current flows through M1 will be mirrored here, right? Right now.
Yes, sir.
So I4, what will be I4? It will flow in this direction, right? So I1 is flowing here, I2 is flowing here like this. So this is going to flow here, I2, correct? And this will be mirrored here in this same manner, correct? But it will not be exactly mirrored because there is CP here. So it will be a function of frequency, correct?
Yes, sir.
So
Yes.
what will it be? Tell me. First of all, I2 is going to flow through GM2, right? So what will be the voltage generated here? First of all, I2 is going to flow through GM3, right? Diode connection here. GM3 parallel CP, correct?
Yes, sir.
So what will be the voltage generated here at this node?
Sir, I2 into 1 over GM3 parallel 1 over SCP.
GM3 plus SCP, right? This
Yes.
is the voltage,
Yes.
correct?
Yes, sir.
Yes.
And then
Yeah.
this will be what? Multiplied by the GM of M4, correct?
Yes, sir.
And that will be the current I4, isn't it?
That would be the current mirror, right?
What?
That will be the current mirror, right?
Yeah, yeah. This is because of this current mirror. This is I4.
Right. Okay. Okay.
Fine. Right now?
Yes, sir.
Yeah. So now tell me what will be the total current here? I2 plus I4, isn't it? Which is leaving this node here. I2 is leaving this and I4 is also leaving this, right? So total current will be what? I2 plus I4 at the output. So total current leaving the output node is what? I2 plus I4. And what is the impedance connected at the output at this node here? What is the impedance?
R0 to 2 parallel R0 4.
No, but R0 is assumed to be infinity, isn't it?
So GM2 into 1 by GM2.
No. I have assumed all the output impedances to be infinity. Tell me what will be the output impedance here at this node?
Sir, 1 by SC.
Yeah, correct. So there is a capacitor here, right?
Okay. Okay.
If this capacitor is not there, then it will be infinity. Okay. Since there is a capacitor, then
Yes.
we have the output resistance is not infinity, it is 1 over SC, right? So this I2 plus I4 will flow through 1 over SC, isn't it? So voltage at the output, which let's call this as some V out. No, this is not V out, this we cannot say it's V out. Let's call this some V out prime. Okay, so at V out at V out prime is equal to what? So I2 plus I4 divided by SC, right? Which is simply
Yes,
equal
sir.
to GM2, and GM2, in this case GM2 and GM1 are exactly same, right? M2 and M1 are exactly identical, so GM2 GM1 are same, correct?
Yeah.
So
Yes.
it will be what? It will be 1 over 2, right? So it will be half of Vt, correct? Right?
Yes, sir.
Right. Fine. And similarly GM3 and GM4 are same, but let's leave it. Yeah, so so I2 here will be what? Vt over 2, right? Oh, sorry. This is not Vt over 2, GM times Vt over 2. GM1 times Vt over 2, right? And here it will be GM1 times Vt over 2 into GM3 divided by GM3 plus SCP. So here also GM4 and GM3 are same, so I have simply replaced GM4 with GM3. Okay, fine. So now it will be total current will be what? GM1 times Vt by 2 plus GM1 times Vt by 2 into GM3 by GM3 plus SCP divided by SC, correct? This is the total voltage at V out prime. So what is V out or V return in this case?
Sir, one doubt. At the point of M3, that
M3,
what the current division is occurring,
there is no
that
current
I2
division.
current.
Oh, current division is not okay. So there is basically this. There is this M3, right? There is this
Yes.
M3 here, which is diode connected, and there is this capacitor CP, and these two are in parallel, isn't it?
So where there I can do the current division also, right? So whatever current flowing through the M3, that will be reflected in M4. Uh,
Yeah, exactly. Yes, exactly. Yes.
so in that case, the current that I2 into 1 by Cp divided by 1 by Gm plus 1 by SCP. Right?
I didn't get it. Okay,
The
so one second.
the formula for current division.
Okay, so what is the formula of current division? It will be here GM3 divided by GM3 plus SCP, right?
Just
Right. Right now.
yeah.
This is the
Yes.
current that will come out. I4 will be GM3 divided by GM3 plus SCP into
Okay.
I2.
Yes.
So this is what I have written here, right? This is what I have written. GM4 and GM3 are exactly same, correct?
Okay.
This is exactly same, right?
Yes, sir.
Right now.
Yes.
Yeah. Fine. Anyway, so yeah, so this is V out prime we have already found out. So what is V return? Exactly same, isn't it? This is the buffer of gain 1. So whatever is appearing here, it will simply appear here, right?
Yes, sir.
Yeah. So V return is basically GM1 times Vt by 2 plus GM1 times Vt by 2 into GM3 divided by gm3 plus scp divided by sc, and so what will be returned by vt? It will be correct.
Yes, sir.
So this is basically loop gain. Fine. So now tell me how many poles are there in this loop gain expression?
Sir,
Yeah.
Uh,
sir,
poles.
why a negative sign not come in this equation?
Oh, I didn't take this. I mean, here there should have been negative sign here. The
Okay.
output voltage here should have been minus of this.
Yes, sir. Yes.
Okay, so I just ignored it. I mean, I guess that is fine. Okay. Okay, so let's do this. Let's not leave any ambiguity here. There will be negative sign here. Okay. Fine. So tell me how many poles are there in the system?
To two poles.
Correct. So what are the two poles? One is at 0, right? Other one is at
Yes.
Yes, sir.
M3 by C.
GM3 by CP.
correct. And how many zeros?
10.
At what frequency? You can do this right from here. Take gm1 by 2 common. So from here take gm1 by 2 common. So let's solve this. So for z, so let's we return by v out. Vt is equal to what? Gm1 by 2 1 plus gm3 divided by gm3 plus scp divided by sc. So this will become what? So 2 gm3 plus scp divided by gm3 plus scp. Fine. Divided by s into sc, then it will be gm1 by 2. Correct. So
Yes, sir.
the 0 is at what?
2 GM3 by CP.
Correct. Yeah. So this is fine, right? So you understand the reason that why there is a 0 in this particular loop gain expression? You see this?
Because to
Two
two
parallel
paths.
path from input to output.
Yeah, definitely yes. Because there is this path, direct path, right? And then there is this path, correct? And
Yes,
this path
and
is
that are frequency dependent path.
yeah, and this path is what? This path is frequency dependent, right?
Yes.
And this path is not. So that is why there is two different paths with different phase shifts. That is why there is a 0, correct? Also, you could have
Yes,
seen
sir.
from this GM expression, this GM graph, you can see that at very DC, at around DC, this is GM, right? Effective GM is GM 1, and at very high frequency, it becomes GM1 by 2, right? So you see that it is here there would have been a pole, right? And here there would have been a 0, correct?
Yes, sir.
So
Yes.
this is the 0 that
Yes.
basically you can see it from multiple perspectives. That is what I'm trying to say.
Yes. Yes, sir. Yes. Nice. Yes.
Yeah. So go on. So this is also fine. Yeah. So what is the loop, UGB of the loop? Tell me, what is the UGB of this particular loop gain expression? So this is the loop gain expression, right? So L of S is minus 2 GM3 plus SCP divided by GM3 plus SCP into GM by 2 into 1 over SC, right? So what is the UGB? For this, you see, assume two cases where both the parasitic poles and zeros due to CP are below UGB and beyond UGB of the loop. So you can assume two cases here, okay? One case in which all the poles and zeros will be inside UGB, okay? And one case where all the poles and zeros are outside UGB. So you see that there are two poles, right? We have two poles, right? These are the two poles. So one pole is at origin, there is nothing you can do about. But this second pole, you can this second pole and this second zero, you can assume two things about it. Either they are beyond UGB or below UGB, and these two cases are different design choices. Okay, so tell me what will be the UGB in both the cases. Or let's leave it. I mean, this is fairly simple, so I guess you will be able to do it. Let's you do it in your free time. Okay.
But UGB is like unity gain bandwidth.
Yeah, unity gain frequency. So when
Oh,
loop gain magnitude becomes equal to 1.
yes.
Okay, so I guess you'll be able to do it.
So when it outside, when the poles and zeros are outside the UGB, in that case, from the expression, we can ignore them, right?
Yeah, so basically, for the case where poles and zeros are outside UGB, you can assume that around UGB, this SCP and SCP term here are not there. Okay.
So in that case, it will be simply GM by.
Yeah, it will be very easy. Yes. So basically,
PM by CS.
case 1 is when poles and 0 pole and 0 are beyond UGB. So in this case, your L of S will be what? L of omega u. Okay, the magnitude of L of omega u will be what? 2 gm3
GM.
divided by gm3 into gm by 2 gm1 by 2 into c. That has to be equal to 1. That has to be equal to 1. This goes away. Fine. This and this goes away. It will be simply gm1 by c. gm1. Oh, sorry. Oh, sorry. I have made a mistake here. Yeah, sorry. This is actually omega u here. It's equal to 1. So it should be omega u has to be gm1 by c. Fine.
Yes.
And then comes a case 2. So that you do yourself. When pole and 0 are inside UGB. You do it yourself, okay? Fine. So there is no doubt in this one.
Hello, sir.
Yeah.
Hello. Yes, sir. In this case, is there any intuitive way to find out the zero? I mean, the exact value of zero.
Yeah. So that is what now you can if you directly want to find the zero, you can see that zero is because of two paths, right? Two different paths. Correct.
Yes, sir.
Right. So you see that there is one this path here, and then there is this path. So, and you know that at zero frequency the output will be grounded, isn't it?
Yes.
This output will be 0, correct? Correct now?
Yes, sir.
Correct. So what you can do is,
Yes, sir.
what you can do it is you can this is grounded, right? So you can assume that you can apply a test voltage VT here, fine, and find out what will be the current coming here and what is the current coming here, and simply equate them. Sorry,
Okay, sir. Understood.
add them and equate to 0. That is one direct way to find the zeros. Okay.
Yes, sir. Yes, sir.
One doubt.
Yeah.
So for the expression of I2,
I2.
yeah, for the expression of I2,
Where is that?
try that one again. I2 is GM2 by 1 plus 1 by GM1.
Oh, this one.
That is source, we consider source degeneration, right?
Yeah, right.
So what about the impedances which are looking into the source drain of M3?
Yeah. So right. So this expression here is 1 over GM1. Looking into source of M1, the impedance is approximately 1 over GM1. This is an approximation. Okay. This is almost always valid when there is no, when the impedance here, whatever connect. So okay. So this is not good. So if you have this case, this is, let's say this is some RD. Okay. there is this some transistor M0, and there is some current source here, and let's say
Oh
this is
yes,
ground.
yes, I've understood. Understood. Yeah, yeah, yeah. Understand because there's like that current source will directly go into the resistance, right?
No,
So
no,
that's
no, no.
why.
Let me make my point. Okay.
Okay.
Okay. So yeah. So what I'm trying to say is that in this particular situation, if you want to find out what is the looking in impedance here, R out. Okay. So it is always almost equal to 1 over Gm. Fine. As long as this Rd is not equal to infinity. If this Rd is not equal to infinity, then the looking in impedance here is almost equal to 1 over Gm. Okay.
Okay.
And you see that in this case also, at the drain of M1, right, is whatever is connected is not infinity, isn't it? It's a
No.
diode connection here. It's a diode connection here, right?
Yeah, and the capacitance will
And that is also not infinity, right? I mean,
not
capacitance.
really.
So that is why uh, looking in impedance here will be 1 over Gm1. Okay, it can be approximately equal to 1 over Gm. Fine.
Yeah. Okay.
All right. So let's move on. Okay. Let's see. Let's do this. Or let's leave this. You do this yourself. Let's do this. So in this first problem, what is the ratio V1 by V2? V2 by V1? This figure A. If this capacitor is not there, what is the ratio?
R2 by R1 plus R2.
Right? Is that DC? Okay? Right? Now what is the exact expression V2 by V1 as a function of basically in Laplace domain? What is the exact expression? This will be 1 over R2, sorry, this R2 parallel 1 over SC2, right, divided by what? R1 plus R2 parallel 1 over SC2, correct?
Yes, sir.
What will it be? What is R2 parallel 1 over SC2?
R by 1 plus SC2.
R2 by 1 plus SC2 R2, right?
Yes.
Divided by R1 plus R2 divided by 1 plus SC2 R2, correct? What will it be? So be R2 divided by R1 plus, sorry, R2 plus R1 plus SC2 R1 R2, correct? Is it correct?
Yes, sir.
And what will it be? Simplified version of this, it will be R2 divided by R2 plus R1, like this, R1 plus R2 to 1 divided by 1 plus SC2 into R1 R2 divided by R1 plus R2, right?
Yes. Yes.
So what is the intuition behind this result? So what is the pole location?
Sir, R1 1 over R1 parallel R2 into C.
So the pole in this question, in this particular situation is C2 into R1 parallel R2, right? 1 over, correct?
Yes, sir.
So what is the,
Yes, sir.
how could you directly see this? Fairly
Sir,
easy,
we,
right? V1,
yes.
if you ground it, you see that R1 and R2 are in parallel to each other, right?
Yes,
Yes.
sir.
And then they are parallel to C2 also. So this is fairly easy, right? Fine. Now, I mean, could you directly say that there is a pole in the system without solving the without even
Yes,
solving
sir.
it?
Yes,
What
sir.
is the
Yes, sir.
intuition behind
Yes,
that?
sir.
How could you directly say that there is a pole in the
And,
system?
at least sir one storage element like independent
Correct, correct,
state variable.
correct, correct. Other thing is that you see that there is a frequency dependence in the response, right? V2 at DC is equal to R2 by R1 plus R2, right? V2 at DC is R2 by R1 plus
Yes,
R2. But at infinite frequency, at very large frequency, V2 will be grounded, right? Because
yes,
of this
yes, sir.
capacitor C2,
Yes,
V2 will be grounded. So you can say that there will be something of this kind. The response will be something of this kind, right? So there has to be a pole in the system. Can there be a zero in the system? Could you directly say that from looking at the figure?
yes, sir. There will be no zero.
Why? Because
That there is no instantaneous change in the output, like
that is a very good explanation, right? Correct.
time domain in the time
But
domain.
yeah, that is a very good explanation. But yeah, that is actually a good explanation, right? But in the other explanation can be what you see that there it is what it is always going down. The response at infinite frequency is zero, right?
Yes,
So the response here it will be grounded at infinite frequency. So there is no option of if there would have been a zero, this would not have been the case, isn't it?
yes, yes, yes. The slope will be increasing. Yes.
Yeah. So fine. So now let's say I want to make, so this is let's say I wanted to make a resistor divider. Okay, I wanted to make only this thing. I wanted to make only resistor divider R1 and then R2. But this R2, when I tried to implement it, it came with its own parasitics. Okay, so a resistor divider. What is the purpose of a resistor divider? To get a frequency independent division of voltage, right?
Yes, yes,
So this V2 here,
Yes, sir.
I want it to be some constant times V1, right? And it should not change with frequency, correct? But because of this parasitic capacitance, now there is a frequency dependence, isn't it?
yes, sir.
But I do not want that in this particular case. I do not like that frequency dependence here. So what should I do to get rid of that problem? So my question is, what should I do here? What changes can I do here in this circuit so that I get a V2 by V1 ratio which is independent of frequency?
So we should introduce a zero
Correct,
at
correct.
the
And how can I do that?
capacitor parallel to R1.
Right. So why did you think that?
Because in this case, two parallel path is there and frequency dependent. So once the zero will come and that zero will cancel the
So
pole
yeah.
if
So
we set the
basically,
value.
correct, correct, correct. So there now there will be now you can see that in this case also there are two frequency dependent. So what is the recipe of a zero? You have to have two frequency dependent paths, right? They have to add, correct? So generally you have seen it in terms of this current added in the frequency domain, right? Two different phase shifted currents are adding, and that forms a zero, right? But here is what is happening here. Two voltages are added here in this case. Hello, are you there?
Yes, sir. Yes.
You see the
Yes.
voltage drop across this particular part and this particular part. These two are adding, and they can add to form a zero. Okay. Generally, what have you seen? You have seen generally two current sources, right? The two currents which are adding. So in the famous this thing, two-stage Miller compensation, there also we had the current thing, right? There was this current and there was this current, correct? These two were adding, right,
Yes, sir.
to form a zero. But here it is not the current which are adding to form a zero, but the voltages. So the voltage between this one and this one, these two will add to form a zero.
So, sir,
Sorry,
in this case,
fine. Sorry. I made a mistake. Sorry. That is not the case here. Here also there is a current only. Here also current is only adding. Okay. I'm sorry. I made a mistake. That was not right. So here also current only adds to form a zero. Forget about whatever I said. Here also current only adds. Okay. What is the location of zero in this case? Can anyone say?
Sir, 1 by R1 C1, like.
Yes, it will be 1 over R1 C1. Yes. Yes, yes, exactly. It will be 1 over R1 C1. You see,
Yes, yes.
at the location of 0, this will become 0, right?
Yes, sir.
Yes.
Yes.
So whatever current comes here and comes here, they have to simply, this will simply loop inside, right? So it will be 1 over R1
Yes.
C1. Yeah, I whatever I said, please forget that. Uh, that is not applicable here. Fine. Okay, so you said that there has to be 0 in this particular thing. So how should the 0 be located so that it I get rid of that frequency dependence?
So the zero should
Sir,
be
it is
equal
same
to
to the.
the pole.
Yeah. So
Yes.
exactly. So in this case, the pole is equal to what? 1 over R1 R2 divided by, yeah. So by the way, what will be the pole? New pole. Pole will be affected, right?
Yes, sir.
Yes,
So
sir.
what is the pole?
So 1 by C1 plus C2
Yeah.
into R1 by parallel R2.
Yeah. Correct. And what is 0? 0 is 1 over R1 C1. Correct. And they have to be same, equal to each other, right?
Yes, sir.
Yes, sir.
Yeah. And when you ensure that, then you will be able to restore the frequency independence. Okay. So there are multiple ways to see this particular thing here. You know that one of you said that there was a pole in this system without C1, without this capacitor C1 here, there was a pole in this system, right? Because instantaneously voltage cannot change, right? When you apply a unit step here, the voltage V2 will slowly rise, right?
Yes, sir.
Without capacitor C1, fine. But now what do you want to have? If you want to have, if there was no frequency dependence in the circuit, then in response to this instantaneous voltage here, the voltage V out V2 should also be instantaneous, right?
Yes, sir.
But now it is lagging slightly. Now it is going slightly like this. So what do? You make sure that there is a system, there is something in the system which is going to do that instantaneous business here, right? And that is done by a 0, correct?
Yes, sir.
So one second. Yeah. So what do? You add a 0 in this system, and how do you add a 0? You add a fast path, right? So this system was slowed down, right, because of this R1 and this capacitor C2. But if there is a capacitor bypassing this resistor R, and you know that capacitor has the ability to become a short at infinite frequency, right?
Yes, sir.
A unit step at this part, the sudden rise is like a very high frequency signal, right?
Yes, sir.
So you want to have the sudden rise at the output also. So you effectively want to bypass this R1, right? You want to
Yes.
short the input and output effectively in that case, right? So that is why you added a capacitor here. This capacitor, it effectively bypasses this R1 and creates a sudden jump at the output. Okay. So this is the intuition behind adding a capacitor to make sure that the system has a 0, or basically whatever way you like to understand it. This is another way to understand. Okay.
How do you get the position of the 0 1 by R1 C1?
Okay. So that is fine. So what I did was, at the location of 0, you know that V2 by V1 of S at 0 should be what? 0, right?
Yeah.
Correct.
Yeah.
So
Yeah.
V2 will be 0, correct?
Oh, okay.
Now if the V2 is 0, what is the current flowing through this C1? It is V1 by SC1, right?
Yeah.
And what is the current flowing through R1? It is
1 by R1.
V1 by R1, right? Correct.
Yeah.
Now
Yes.
both the currents, they have to be add to equal to 0, isn't it?
Yes. Yeah. Yes.
When you do this, you will find out that S was equal to 1 over R1 C1. Okay?
Okay.
Yeah, fine. So this is a very neat way to make. So did you understand the main concept here and intuition behind adding capacitor here, C1?
Yes, sir.
What is the
Yes.
intuition behind adding a? I mean, how does it form a 0? So this is basically acting like a fast path. It will provide the sudden jump. Okay? Yeah, fine. So now let's deal with this question here. So in this case also, so this is a very frequent problem. So what I'm going to talk about it. So this is basically an op amp here inside, right? This is an op amp here. This is an op amp here, and you have put it in negative feedback. Okay, this is a normal negative feedback. Ignore this capacitor for now. Okay, ignore this capacitor for now. Just ignore this capacitor for now. So without this capacitor, this R and this R, they are basically, this is basically a unity gain this thing, right? This is a unity gain thing. This op amp, let's assume that this is a very high gain, and without this capacitor CP, what will be the response? V out by Vi -1, right?
Yes, sir.
Is that understood?
Yes, sir. Yes.
Now you know that this op amp is non-ideal, right? It cannot be an ideal op amp. It will have some unity gain frequency, it will have some poles inside it, right? All those things will be there with the op amp, correct? Now you have what you did, you went ahead and you designed this op amp very carefully so that phase margin is very good and everything is very fine, right? Now what happens when you connected it in this fashion? You saw that everything went haywire and your phase margin decreased suddenly. So what could be the reason of that?
So due to resistive load, like,
No, let's say this resistance was accounted. Okay, this resistance was accounted for. So how do you find phase margin in this case? How do you find the open loop gain? So you do this, right? I mean, this is your op amp. Let me use a different color here. This is your op amp, okay, and this was the resistor. And this was grounded. This is V in, this is V out. So how do you find the phase margin? You first break the loop, right? Or first you have to ground it, correct? Then you break the loop and you apply an input here, V test, and you find out what is coming here, V return, correct? That is how you find out. Let's say you did this, okay, you did this analysis and you saw that everything was fine, okay, but yeah, you did this and you saw that everything was fine at that time, but when you connected it like this, you saw that system was unstable, it was not settling. So clearly there was something wrong, right? So what do you think could go wrong here? Do you understand my question? Do you understand my question?
yes, sir. Understood. Yes.
So what I was saying is that this is V test applied at its input here, okay. You saw what is V return and you calculated V return by V test, and you saw that this is basically the loop gain, right? And you saw that loop gain has you designed it such that the loop gain is very good and phase margin is also very good, everything is fine. But now when you connected it in the closed loop manner, in the closed loop like this, you saw that the system is actually not stable. So whatever phase margin you were getting, there was something fishy with that. I mean, that was not very correct. That was not the correct phase margin. So why was it not the correct phase margin? What could have gone wrong? So look at this. So this capacitor, right? This CP here. This capacitor CP here. Can you look at it?
Yes, sir.
This capacitor CP here is not something which you accounted for earlier. So when you do this CP can appear because of the parasitics of this thing, input stage of this op amp. Okay, this op amp will be realized using some transistors, right?
Okay.
Yes, sir.
So this
CP is
input
making
here,
a non-infinite pulse.
so so basically this input here, this input IN plus and IN minus, this will be having some CGS here, right? CGS here and CGS here also, right? These capacitors can be present here, correct? But when you opened this and when you applied a test voltage here, you didn't account for this capacitor CGS, right? You didn't do that. You simply calculated V return and by VT. You didn't account for the CGS here. Okay, and the CGS can be very large, and they can create very lot of problems here. So what happens to do the CGS effectively?
Sir, extra pole.
The CGS appear here, right? Effectively, correct?
Yes, sir.
And this CGS here, it appears here, and the correct way to open the loop would have been like this, right? The CGS should have been a part of this particular part, right? And applied V test here, and look at V return here. If you had done that, then you would have gotten the correct loop gain expression, because right. So if you do this,
Yes.
then you will get the correct loop gain expression. So what will happen because of CGS? You will get an extra pole, right?
Yes, sir.
Right?
Yes.
Fine. So this pole is definitely not desirable. This can be very low frequencies, because this resistance R is generally very large. Okay. So this due to the CGS, the pole that can appear because of this R and CGS, it can come at very low frequency, and this is not desirable. So what will you do?
So the resistance value we can increase.
No, if you increase the resistance value, then it will come at even lower frequencies.
Okay, okay. Then we can decrease it one by R.
No,
So.
you cannot go on decreasing it, because what happens? You only said, right, that this resistance here will start to load this particular op amp, isn't it?
Yes, sir.
So you cannot go on decreasing it. It is true, you can decrease it, but you cannot go on decreasing it. Let's say we have decreased it to the least value that we can tolerate, but even then the loop is not stable. The CGS is not. Basically the pole due to CGS and R is still inside the loop gain, and that is not tolerable. So what will you do then?
Sir, we can add one fast path and cancel one pole.
Yes, exactly. So what you can do is you can put a capacitor here. Okay. And what will be the value of this capacitor?
Sir, CGS.
Yes, it will be CGS only. Basically, it will be CGS since this R and R are same. Okay, this would have been R2, this would have been R1, then this would have been some different capacitor CGS.
Yes.
Okay, fine. So you understand this, right? Everyone understood why I am adding a capacitor CGS here.
Yes, sir.
Yes, sir.
Because now, because of CGS, this becomes a fast path. Effectively from V out to V return, this I wanted to be a voltage divider, isn't it? You see, from V out here to this node here, I simply want a voltage divider, right?
Yes, sir.
But because of this capacitor CP, I get a frequency dependence in that voltage divider, kind of like this, the previous one, this particular example, isn't it? So I want to eliminate that frequency dependence. So what will I do? I'll simply add a fast path here. Correct?
Yes, sir.
Yes, sir.
Yeah. So this is actually a very frequent problem, and people generally have to do this. They have to put a capacitor here to get rid of this problem. Okay? Is that understood?
Yes, sir.
Yes, sir.
Yeah. So, but there is a catch, by the way. So can you tell me what is the problem here of adding this capacitor here? One can say that now, since I can always eliminate this capacitor, eliminate the effect of this capacitor CGS by simply adding an equal capacitance here. So I can keep on increasing the size here, right, at the input. I can tolerate very large capacitances also, right? It seems like this. I can tolerate even infinite capacitance at this node if I add an infinite capacitance here. So what is the catch here? Definitely this looks too good to be true, right? So what should be the catch here?
It adds another pole, sir.
No, not exactly. It does not add any pole in loop gain expression. Sorry.
Sir, resistor
Yeah, go on.
sir, resistor mismatch.
Yeah, those things are there, but let's say that is also okay. I mean, those things are there, but let's say that is okay. But so the catch is that think from the closed loop perspective. In the closed loop, what happens? So now earlier it would have been like this.
Sir, will it affect the output impedance?
Uh,
Like it is a Miller cap.
no, no, it is in the loop, in the open loop case, in the loop gain expression, everything will be improved because of
Okay,
this CGS, okay?
okay,
But
okay.
something else happens in the closed loop. So earlier the situation was like this, okay? This was R, okay? There was a capacitor C and CP, and because of that you added this capacitor CP is not. So this is like this. This is CP, okay? Now what happened? You changed it to this situation here. This is R. So R. We added a capacitor here. CP. So and this resistor.
Sir, at high frequencies, voltage gain is zero, sir.
Yes, exactly. Yes, very good. So what happens in the closed loop? You see that earlier the gain between V out and V in was what? -1, right? Right now.
Yes,
Yes,
sir.
sir. Yes.
But here in this case, you see V out by V in is now has another pole because of this CP and R, right? So you can clearly see that at very high frequency, this CP will be shorted, isn't it? And since this is grounded, so this will also be grounded. So effectively, gain will be zero. V out by V in gain will be zero at very high frequencies.
Yes, sir. Understood. Yes.
So what happens is that there is another pole in the closed loop because of CP, and that pole is 1 over R into CP. Okay. In the closed loop, pole is at this 1 over R into CP. So if you keep on increasing CP, you will see that your closed loop bandwidth will keep on decreasing. So you cannot play this game forever. I mean, there is going to be a certain limit on CP. This maximum tolerable CP. Okay, based on whatever closed loop bandwidth you are targeting. Okay,
Yes, sir.
fine. So I guess that's it for today, and we'll meet again next Sunday. That will be the last tutorial in this
Sir,
particular.
one doubt, sir.
Yeah.
Sir, can you go to screenshot of that noise effect, sir?
This one.
Yeah, here, sir, in current division, it is showing that 1 by RS plus 1 by RS plus GM, sir.
Where is 1 by RS plus 1 by RS plus GM?
In right side, sir. Noise contribution of M naught in right side, sir.
Okay, this one.
Yes, sir.
1 by R is divided by 1 by RS plus GM. Yes.
Sir, here we are talking about the current going through transistor, no, sir?
No, 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 no. I am talking about the current that is going inside this short circuit path here. This one. So what current will go inside this short circuit path?
RS current.
You see this current here,
Yes.
this current here,
Yes, sir.
this current here. It has two paths here, right?
Yes, sir.
One is going here, one is going here.
Yes, sir.
Whatever is going inside in this transistor will again come back here, right?
Okay, sir. Yes,
But
sir.
whatever is going inside RS, it is going into ground, and from ground it will come back in this direction, right?
Yeah. Yes, sir.
So whatever is going into RS will come back from the ground,
Yeah.
isn't it?
Yes,
That is
sir.
why it is that particular current which I am talking about.
Yes,
Okay.
sir. Thanks. Thank you, sir.
Yeah. So I guess that is fine for today. I mean, we'll meet again next Sunday, and thank you everyone for joining. So next Sunday, prepare your doubts. So next Sunday will be only discussion. I will not be taking any questions. I will not be covering. I will not be covering my own questions. You can come up with your questions and I will discuss them. Okay.
Sir,
Yeah,
at the beginning, I'll talk
at the
current
beginning,
injection. Current injection. Yeah,
current
sir,
what?
the high frequency electrical circuits.
Yeah. So yeah. So you wanted to ask something. Yeah.
Yes, yes, sir.
So what is it?
Yes, sir. Sir, that will I think at the end recently they uploaded, sir, that non-linear currents is there, sir. Non-linear currents and current injection method. First
Oh,
order, second order.
yeah. I understand. Yes. So
Yes, sir. Can I implement in LT Spice, sir?
I do not know. I have not tried it. Uh,
I
I do
mean,
not know whether there is an option of creating that. I mean, whether there is an option of polynomial currents, because you require this higher order currents, right?
yes, sir.
Power
Second order
3,
and
power
yes, yes,
3,
sir.
power 2, all those things. I do
Yes, sir.
not know whether that is possible. I do not know actually. Sorry.
Sir, we can. Is there any way to implement, sir? Analytically, we can write. Is there any way to implement this through simulation?
Uh,
Could you please guide me, sir? I would like to present, sir. I have one fellowship, sir. Some IIT Bombay. That's it would be very useful, sir. That's why.
yeah. I have to think about it. Okay. In the next
Okay.
session, I will talk about it. Okay. If
Yeah.
I find a solution, I'll think about it. If I find a solution, I will talk about it in the next session. Okay. You
Okay.
please remind
And
me again in the next session.
yes, sir. Sure, sir. Thank you, sir.
We'll talk about it. Yes.
So sir, I have one question.
Yeah. Yeah. Go on. Hello. Your voice is cracking. I
The
can't hear you.
last problem you have discussed. Hello,
Yeah.
hello, can you hear me now?
Yeah. Go on.
Okay, so the last question, I go to the
This one.
yes, yes. In the yes, sir. In this question, so the CGS you are talking about. So in this CGS, can I include the capacitance of CDG? I mean, by
CDG.
Miller effect. Yes,
Yeah. This
sir.
that will be there. Yes. That is actually a very important part. That
Okay,
will
okay.
also be very dominant thing. CDG will also be there here. See GD. Yes. CGD will be there, and that will
By
also.
Miller effect.
Yeah. That will be actually multiplied by the Miller effect. Yes. That is indeed present, and that is
Yes,
going to create a lot of problems. Yes.
yes, sir. Okay, sir. Thank you, sir.
Yeah. Okay. So guys, let's call it a day for today. Fine. We'll again meet next Sunday. Fine.
Okay. Thank you, sir.
Thank you. Thank you. Thank you all for joining.
So thank you, sir.
Thank you. Thank you, sir.